Today we're counting the ways through a cave system. Initially we're given a list of connections. For example, start is connected to A and also to B, A is connected to B and also to C, and so on. And if you stare at this for a couple of seconds, you will probably see one or multiple ways from start to end. Okay, so that's one possible representation, basically a list of pairs, and I also wrote a type for that in C++. So a connection is a pair from string to string, and then since I need vectors of those connections in multiple places, I made another type for that. So the singular is the pair, and the plural is the vector of those pairs. Okay, so that's one possible representation, and another representation would be a multi-map from string to string. Maybe let's look at the Clojure example here. So basically we take this list of pairs and then we convert it in Clojure to a map that maps from start to all reachable caves directly from start. So you can see these two lines basically turn into this one line. Okay, and this is in some sense a simulation of multi-maps where a key is mapped to a container of multiple values, but from the point of view of the map, it's just a single value. In C++, multi-maps are in the standard library. So I can say I have a mapping from start to A and also a mapping from start to B. That's not a problem. Okay, and what you can also see is, so here in the list of connections, the order didn't matter. So it didn't matter if I wrote A, B, or B, A. This meant a bidirectional connection. And here in the second representation, I have to store both ways basically. So A is connected to B and B is also connected backwards to A. The only exception is the start string. That will only ever occur as the key. We never want to go back to start. That simplifies part 2 a bit. Okay, so here first we convert the flat list into pairs of 2. I already did that in the C++ version, so no need to do that. And then, yeah, here we have a functional way of building that map. The interesting part is here. So ordinarily, we want to put both directions into the map from A to B and also from B to A. The exception is the start cave. So if A is the start cave, then we only want to map from it and the other mapping is missing. And if B is the start cave, then we only want to map from it. The other mapping is missing here. Okay, so that should be rather straightforward. Maybe let's write that here. So that would be connections to system, const connections, and then we for each over that. So that would be, of course we need a result. So let's say system, and then later we're going to return that. Okay. And then maybe let's implement the default case first, where we insert both directions. That would be system in place, connection first, connection second. So that's how you access the elements of a pair. So that would be A and B basically in the Clojure version. And then also system in place, connection second, connection first. Okay, and now we have to prevent connection second from being start here and connection first from being start here. So let's just do a simple if statement. So if connection second isn't start, then we want to perform this emplacement. And similarly, if connection first isn't start, then we want to perform this emplacement, ensuring that we don't map to start. So all this connections second and connections first, maybe that's a bit unreadable. It would be much nicer if we could call it A and B. Okay, cool. So that would be that. Then what's the next function that we have to implement? Oh yeah, so some caves are big. They start with an uppercase letter. Some caves are small. They start with a lowercase letter. So we simply have to look at the first character and then see if that is in uppercase. So that would be big cave of string. Okay, and then we simply see if cave at 0, and I'm going to cheat a little bit. I'm just going to see if it's less than the ASCII code of the small a, because small a is 97 and big A is 65. Okay. Yeah, and then we already come to part 1. How many paths visit small caves at most once? Let's see how we do it here. So that's a recursive algorithm. So here is a function that bootstraps the recursion, that says we convert from connections to system and then start from the start cave, basically. So I can already write that overload. Okay, so that's simply bootstrapping the recursion. So let's write the other overload here. So that would be, okay, cool. Now what do we do here? First we check if we have reached the end, if cave is the end, and then we simply return 1, because that's basically one additional way that we have found. So that's a simple if the cave is the end, then we return 1. Otherwise, what do we do? So first we determine the neighbors of the cave. That's a simple map lookup. So something like system. In multi-maps, we don't want a single element. We need to get an entire range of all the mapped values. So how do we do that? That would be equal range of the cave. Okay, and now we get back a pair of iterators. So that would be, let's say, so this is really nice for functions that return pairs to immediately get at the components, basically. Okay, so that would be the neighbors. What else do we do? Yeah, and then we compute the subsystem. So if we have a big cave, we just use the same system as before. Otherwise, we compute a new map where the cave isn't contained as a key anymore. What do we do in the normal case? Let's see. So here we have a transduce where we basically loop over all the neighbors, add them up starting from 0, but we don't add the neighbors themselves up. First, we map through a recursive call to ourselves with that neighbor. Transform reduce, like this. And then we pass in the begin and the end. Then we pass in 0, then the plus operator, basically. And then we pass in a function that is applied to all the neighbors before the result is added up. So that would be a function that takes a neighbor. That's a string. Let's call it nay for now. Okay. And now comes the recursive call. That would be the recursive call here. So that would be part 1 of the unchanged system and then the neighbor. Okay, so that should work. Let me quickly compile so make sure. Of course, we did something stupid. System is not captured. Ah, okay, that's interesting. So here we use the parameter nay, which is just part of the lambda parameter list. And if we also want to use the system, previously I explained, then we have to write it here in the capture list. But that would make an unnecessary copy of the system. So we precede it with an ampersand, and then we will capture it by reference. Let's see if that works. Okay, what did we do wrong now? Ah, right, so the begin-end range doesn't just contain the values, it's a sequence or a range of pairs of key value. So let me do that with an auto. That would be a pair. And then here we have pair dot second. That would be the value. Okay, let's see if that works. Right, and then we just have the control reaches end of non-void function, because in the else branch we don't do anything yet and we forgot to return the result of transform reduce. Okay, so then let me simply copy paste this into the else branch, and then we have to use the copy instead of the system. So basically that would be the copy here and the copy here. Okay, let's see if that compiles, if the warning is now also gone. Okay, cool. Yeah, and I think then we could check if that works, right? So what is part 1 of demo connections A, and then the same for B and C, because we know all the expected values. That would be 10, 19, and 226. Let's see if that works. We don't get anything, so probably another memory corruption error. All right, so these begin and end iterators belong to the system cave system. Here we make a copy and then we use the same iterators to erase from the copy. Of course, that's illegal. Yeah, here I think I can simply say erase and then the cave. I think that also works. I don't think I really need the iterators here. Let's see if that works. Okay, that's nice. Those are the correct numbers. Yeah. Okay, then on to part 2. Here the twist is a single small cave can be visited at most twice. So initially we could only visit each one once. Here's one exception. And how do we do that here? So yeah, first we have this bootstrap process again. So maybe let's just copy paste here and say part 2 bootstraps the part 2. Yeah, that's basically almost the same, but we need more arguments. So I have 2 additional arguments here, a set of visited small caves, and then another boolean that says, can we visit a small cave twice, or have we already used that credit, basically. Okay, cool. And then part 2 would be a system, then a cave, and then we have a set of string, let's call it visited, and then our credit. Okay, and maybe let's already call the function for later and just return some dummy value for now. Okay, so what do we do here? Right, so basically we have a big if-else, if you will. If we have reached the end, then again we return 1. Maybe you can already implement that. Then we see if it's a big cave, then there are absolutely no restrictions. So if big cave of cave. Okay, so we have to extract the neighbors first again. We did that with our nice line here. Let's copy paste that like this. Okay, and then we have a transduce again. Maybe we should copy paste that as well, so we don't do any silly mistakes, and see what we have to change. Do we have to change anything? Yeah, here we have to use part 2, of course, and then we have to pass additional parameters. So, and then the visited, we simply pass it through, and the credit, we simply pass it through, and then we should get exceptions because we don't capture enough, or errors because we don't capture enough. Here, visited is not captured, and credit is not captured. So that would be visited credit. Credit is just a boolean. We can capture that by value. That's fine. Okay, so at least the compile errors are now gone. Okay, so that should be the simple case. Then the next case, if we haven't visited the cave yet, so that would be, what do we want to do then? Then it's a similar transduce, but we make another copy of the visited set where cave is contained. Okay, so alternatively, we could simply add that to the visited set, which we should probably pass by reference so we don't make copies all the time. We could simply insert that into visited, and then after the recursive call, remove it again. That should also work, right? Let's see if that works. So that would be visited and place cave, and then later after the recursive call, erase cave, like this. Okay. And then we have exactly the same transduce as before. Right, so let me simply copy paste this. That should be this. Quite a lot of code. Let's see if that compiles, just to make sure. Okay, that should be erase and not erases. That's here. Okay, was that the only error? No. What else do we have? Cannot bind non-constant array reference. Ah, right, okay. Right. So if we accept a parameter by reference without the const, then we cannot pass in a temporary. That's simply illegal. So we have to put that into its own variable first. So that would be visited. And that also won't work. Let me show you why quickly. That should give us a horrendous compile time error. Yeah, but that's a nice error. So basically it tells us what you have written here is a function declaration. You declared a function that takes no parameters and returns a set of strings. If you remove the parentheses, then it is an empty set basically. And that's exactly what we want. Yeah, so that's a common syntax trap of C++. Okay, and then what's the next case? If we still have credit, else if credit, what do we want to do then? Then we want to do the same thing as in the first case, but credit is replaced with false because we no longer have credit. Credit replaced by false. Yeah, and the default case is 0, so that should be this guy. But I think it's probably nicer if we put that into an else just to be consistent with everything above. But the results should stay the same, 10, 14, 8. Is that something that we would expect? No, that's way too small. Here's our expected values. Ah, of course. So here we return the result, and then here we have dead code. That statement here will never be executed, the visited erase cave. So we have to remember that in a variable, let's say result, then do the erase and then return the result, right? So otherwise the cave will never be erased from the visited set. Let's see if that now works. Oh, 36 is definitely correct. 103, 3509. Yeah, those are the correct numbers. I was a bit surprised that the compiler didn't catch that after the first return, there was another statement.